we are going to discuss on the design of steel concrete composite columns, which is encased and infill. We will see like what is the actual difference in the material takeaways or its capacity resistance. So we are going to talk about concrete encased steel and the tubular steel where the concrete is infilled. So a quick thinking like why should we use composite columns? We have discussed a lot about the advantages of using composite systems, but I would say it is a natural selection. That is what the nature selects. So we have our legs, which is like columns. Like it is like our encased columns, and also we have this lot of layers in our tree trunks. So nature is not struggling much in calculating its capacity, but sometimes we have to do it. And it is not a new concept, composite, it's not a new concept. We can see this Ericsson building in Vienna in 1913 where they have used this encased columns. People have also used infill columns without even knowing that it is going to improve its load-bearing capacity. But it was not widely used back in those days because they were not very sure about the reliability of the capacity which is coming from this particular system. But with the advent of modern technology and calculations, now people have used this system in so many buildings across the world, in India. So let us see how this, these are the topics for discussion. I'll be talking quickly about the pros and cons of encased and infilled systems, the load transfer mechanism, the capacity calculation, composite design. I will take an example. We'll do the example in both the type of cross-section and we'll compare them. And most importantly, the load transfer and load introduction, which is actually going to make this column a composite. And the connection and joint and some myth busters finally. Okay? So concrete encased systems, we know that it has higher load capacity, load-bearing capacity and stiffness. So it is used for high-rise structures and also for seismic resistant design. It has this protection against corrosion, fire, and also this local buckling. On the other hand, concrete filled is also having higher load-bearing capacities, particularly coming from the concrete confinement and improved ductility. And it is also used for high-rise structures and seismic resistant design. And steel buckling is delayed. We cannot say it is completely prohibited, like how we can see in encased, but it is delayed a bit. And there is no need for formwork and for concrete curing. So those are the pros of these two systems. Looking at the cons, so there is a need for the formwork in encased system, and we have to do this concrete curing. And we end up into comparatively larger section because of the provision of concrete cover. And there is a potential for concrete cracking, spalling, and the inspection and repair of the steel becomes difficult since it is encased. And here, the cons in concrete infilled is there is not a complete restraint against buckling or fire. We have to give a little bit of protection, and also it is susceptible for corrosion. So how is the load transfer mechanism works? Based on that, we are coming up with the capacity equations. So when the encased column is subjected to axial load, it is like a springs in parallel system. Both concrete and steel are going to participate. The total load will be the participation of steel as well as concrete. And this is the equation which defines its capacity. It is basically the reinforced concrete column that we have. The equation is the same. However, here we are not having that upper limit of reinforcement which is there in our reinforced concrete systems. Here, code suggests 90% load resistance as the upper limit for our composite. But as such, there is no reinforcement percentage limitation. And no local buckling in the plated steel. Talking about the load transfer mechanism in concrete infill columns, when the concrete infill column is subjected to axial loads, what happens? The steel is coming into biaxial stress condition and the concrete under triaxial stress condition, where the concrete is getting confined and improves the strength. And that particular concrete confinement or the concrete strength enhancement is accounted in this particular formula in our Eurocode. And also, this enhancement is found in the flexural rigidity as well. if you're looking at the reinforced concrete's effective flexural rigidity, this particular factor will be lesser. Here in composite columns, it is larger. It can be as large up to 80% or 90% in American codes. So there's a delay in steel buckling. Concrete strength is getting enhanced. No formwork, no upper limit in your steel percentage. Okay? So these are the long column and short column effects in concrete infill systems. The buckling mode itself is getting changed, which is improving the resistance system. And both the codes are giving the equation, as I have discussed earlier, like where it is targeting in concrete confinement, and it is targeting in avoidance of your steel buckling. And the equations are little bit distinct. But when we are comparing with the test data, we can say that in the practical region, it is more or less the same. But we can use American codes for large D by T, where you can find some economy in your design. So this is the test data comparison with the American equations. For the N-case system, all your test data is lying much ahead of your code equation. And discussing about the beam column design in composite columns, this is the PM interaction given in your Eurocode. You can go using, make this design using the strain equilibrium method, or this simplified method where you are identifying the points A, B, C, and D using this particular axial load and bending moment combinations. And Indian code is actually giving the equation for all these conditions. So what will be the axial load and the bending moment in your, if you take a particular cross section, what will be its axial capacity and its bending capacity at all these points, so that you can just draw this PM interaction curve and see like what is your demand, and you can pick a point and see whether the cross section which you have selected is good enough or not. And when we are comparing the test data, we are taking with different slenderness limits and comparing with the American PM interaction curve. You can see that for large slenderness, this is your cross-section capacity, but for large slenderness, the values are much lesser. The capacity which we are getting from the test is much lesser. So the PM interaction itself is little bit modified as per your American standards. In Euro standards, we are taking this moment magnification. We'll be shortly discussing about that in our worked out example. So here I am picking a example problem from a data center. It came for proof checking. I thought of discussing this in this forum. So it is this is the 3D and the plan view of this data center. It is a G+10 with 2 terrace, which is coming up to this height, 76 meter high. They have chosen a composite structural system with CFST columns and shear walls. You can see the shear walls here. All the shear walls are composite in nature. And the dots that you see, all these are CFST ranging from 600 by 600 to 600 by 900 cross sections of thickness of around 30 mm. So the beam and slab were designed as unpropped systems. Sorry. The server area load, it will be coming around 26 kilopascal. I'm just giving this, to have a understanding like what is the expected loading on this particular system. This spacing is around 10 meter by 10 meter. So if we take one such column from your analysis, this is the analysis results. I am choosing the combination for a gravity load combination in my ultimate limit state, which is 1.5 dead plus live load. And I have taken so that the P max is the larger. There are also some combination where your bending moment is maximum and P is not, but I have just taken this combination for our design problem. So the designers, they have gone with a CFST of tube size 600 by 900 and thickness of the steel tube as 30 mm, and Fy is 450 megapascal. The concrete infill with M30 grade concrete. So for this particular cross section, let us see how to do the design check against this load demands using our IS 11384 code. First, we have to do some basic checks, whether the steel grade, concrete grade, and the cross section which we have chosen is good enough to be called as a composite section or not. So the grade is between 20 and 75, and Fy is less than 460, and the delta, which is the steel participation, load resistant participation, is 0.55, which is between 0.2 and 0.9. And also the B by T limit is coming as 30, which is well within this range which is given in our code of 37.2. See here we have to take care of this epsilon factor. Here we are having Fy of 450, but epsilon, you know, is the square root of 250 by 450, or Fy, whichever it is. And the relative slenderness factor, it is coming around 0.321, so which is less than 2. So we can go ahead with this simplified method of design, and it is applicable for this particular cross-section. So after making this check, next we are going to do this resistance calculation. First, we will start with the compressive strength. Compressive strength is the sum of the steel and concrete strength with the appropriate material safety factors. So this is the cross-section capacity and the critical buckling capacity, applying the actual EI which we are calculating, EI effective. I'm not showing all the equations here. I hope you can understand that. So first we have to check whether the second order analysis to be calculated or to be done for this particular system. So if you're looking at this ED is design effects. I'm just taking the, whatever notation which is given in the Eurocode. So design effect is the actual demands with the load factors. And divided by PCR, it is coming much less than 0.1. There is no need for a second order analysis for this particular column. But we do have to take the column buckling effects in our design. So CFST, it will be belonging to class A of column curve. And from there, I have calculated this as the resistance, the stability reduction factor. And the utilization factor of this for the compressive strength is coming around 0.663. Okay, so that is regarding the compressive strength. Now, let me check for this axial load and the moment effect. For this, we have to draw this PM interaction curve. We can get all these values using the annexure capacity equations, or you can quickly model it in any of your software. So if you take ETAPS, you can just do the modeling, analysis, and design, just for getting the quick points at A, B, and C, D. Okay? So when you get this, for the actual load, for the actual axial load which is coming, you can say that what is your available bending capacity. Okay? So available bending capacity because of the axial load effect divided by the actual bending capacity of your cross-section, that will give you this mu D, mu times D. So then we can use our interaction equation, which is the demand divided by the actual capacity which is available, which is less than 0.8. So our cross-section is safe against this beam column effect. And also I'm doing it in the other direction because it is a biaxial bending. And since it is biaxial, we also have to check this interaction equation. So the combination is less than 1. So we are safe. So whatever cross-section that we are having is safe as per the member resistance point of view. Now I'm going to choose a concrete encased cross-section for the same load demands. I'm picking a cross-section such that my steel section is around the same size as the flange is 600 and the depth is 900. And I'm choosing the flange plate as 30 mm and the web I'm going for 20 mm. Maybe I can do some reductions there. It is not really going to contribute for my bending resistances. So, but still I have to give this rebar and also the cover concrete. So the size increases a bit. It goes up to 1.1 meter by 800 mm. And I'm taking the same concrete grade of M70. I have given 0.8% reinforcement. So for this particular cross-section, we have to do the basic checks again, whether we can use a simplified method or not. So when I do the basic check, material for concrete limit, steel limit, and the steel ratio, resistance ratio, everything is falling under the limit. And for B by T, there is no limits. I don't have any limits because I am having adequate, I'm going to provide adequate shear connectors and also have the covered concrete, so I don't have to check for the B by T limits. Then I'm checking this slenderness limit, the member slenderness limit. It is definitely less than 2. I can use the simplified method of design, but you can see the huge difference between the CFST and the NKs. There it was somewhere around 0.3. Now the member slenderness has increased to 0.6. Even though B by T, it says like local buckling is not going to happen, the member slenderness, it has affected me. Let me see how it is affecting the resistance. So I'm going with the compressive strength calculation. Only difference here is I'm having this extra 0.85 factor for my encased cross-section. So, and also I'm having this reinforcement. I'm adding that as well. Anyway, the cross-section strength is little higher. Cross-section wise, the strength is higher. And also, by the way, the length of the column is 6.5 meters. I forgot to mention about that. And the PCR has reduced a lot because of this member buckling effect that has reduced. And this particular ratio is coming larger than 0.1. So I have to do second order analysis, either in the form of in the analysis itself, or I can give the moment magnification factors. I'm choosing with the moment magnification factors. So first let me check the utilization factor for the compression strength alone. So, and also this buckling class is going down to B and C. That is the most affecting. That is where the member buckling has affected a lot for the N-case ones. And the chi factor has reduced to 0.73. And here is the utilization. It is very, very marginal for my safety. Now let me go and check for the axial load and moment effect. So I can use the code equations for drawing this PM interaction curve. I got all the points, and for this particular axial load demand, I'm checking my MD dash. Okay, I got some value which I'm not showing it here, but before that I want to do this moment magnification factor calculation because I have to take care of this second order analysis effect. Here I got this as a factor for the given P, which is the demand load, and the PCR, the critical buckling load of my cross section, of my member. So this is the interaction equation. I have to increase my demands by this moment magnification factor, and this capacity, I'm reducing it to take account of this axial load effects. Again, it is less than 0.8, so it is much safer in the bending effects because the bending moment itself is very, very less for my column here. So basically the column is safe, the column cross-section which we have chosen is safe, but the utilization ratio for my CFST and encased is quite different. It's only because of this member buckling effect that has affected my encased system. So we have did the basic checks, did the calculation, resistance calculation for compression alone and for taking into account of this beam column effect. Next is to make my composite section a really composite section outside, we have to do this load transfer and load introduction zone checks. See, all these experiments which we have done in the lab, they may say that they did not use the shear connectors because they have loaded it uniformly on this column. Okay, just like how you have with this column cap plate kind of loading system, there your cross section is loaded uniformly, where there is no slippage between your steel and concrete. But if you have a beam which is getting connected to the column like this, the load is transferred only through your steel tube, and by the time it reaches the concrete completely, there might be slippage. There is shear basically. So that has to be accounted. So we can just say that there are three types of loading conditions. One where the load is applied only on the steel tube, only on the concrete, or it is equally transferred. For these two conditions, there is a shear at the interface of the shear and steel and concrete for that to accommodate that particular shear transfer, we have to provide shear connectors, even in CFT specimens, not just the encased one. So I will just discuss like what I have done experimentally. During my PhD, I did this experiment uniformly applying the load or only in the concrete or only in the steel zone. So even the tube is filled with concrete. If I'm applying the load only on the steel tube, you can say that it is behaving just like a steel tube. It is not picking any strength, no higher strength. But if I'm applying only on the concrete, you can see that the stiffness is very, very less initially. Because the concrete has to deform, it is undergoing a lot of deformation before it is hitting the steel wall and getting confined and interacting with the steel. So the stiffness is lesser. But if the load is transferred uniformly on concrete as well as steel, it is having stiffer and very good strength. So we have to make sure that even if the load is getting transferred only through the steel tube or partially on the concrete, shear connector should be provided. This particular shear at the load introduction zone is taken care of. So these are some of the failure modes which I have observed during the experiment. So let us see how the codes are addressing it. So AIC is saying that for encased one, at the load introduction, we have to provide shear connectors. 2 times B, where B is the width of your column, 2 times B at the top and the bottom. Whichever shear, we know what is the shear which is getting transferred from the beam to the column. For that shear, you have to provide the shear connectors, design it and provide. And this load introduction is needed only for CFST, but not all along the length of the CFST column. The shear connector is needed only at the load introduction zone. That is what ASC is saying. There is a small difference between the Eurocode length, like what it is suggesting and what ASC is suggesting. ASC is saying that shear connector should be given to be at the top of the beam and also at the bottom, top and bottom both. Eurocode is giving provision only for the bottom side, but because I would say AAC is much advanced, it is taking into account of the latest experimental data and those evidences. Based on that, it is asking to give shear connectors both at the top as well as bottom when there is a load introduction zone. So if I have to summarize, like what is the shear connector difference between this infill and the encased systems? At the load introduction zone, shear connector has to be provided, both for encased as well as the infill columns. For the rest of the column length, encased column requires shear connectors, because in your column there will be some shear effects. Even though if you're saying that a column is having larger axial compression, axial loads, but there will be some moments, some gradient or varying bending moment, which is going to develop some shear forces. To take care of that, we have to provide the shear connectors. But for CFSTs, that particular shear may be taken care by this friction effect in your system itself. So EC4 says that if the shear stress because of the moment gradient or by any other means, if there is a shear in the rest of the column length, if it is more than some limiting shear stresses, then you have to provide the shear connectors. Otherwise, just the friction between the tube and the concrete will take care of it. And this particular, I'm just giving 0.55 just for representation, but there is a table which gives different shear stress limitations for different types of cross sections. So these are the connections. I just wanted to discuss upon, like maybe I have already discussed in the morning session. I was telling that bolted connections are definitely needed when we are going for systems which is going to have fatigue loads or seismic loads. So the research is still developing, and because you know the bolted system, it is not providing a rigid connection. It is mostly falling in your semi-rigid zone. It is still developing like how to provide a best rigid connection. So one of my students is also working in a different type of connection system where we are having inner steel tube and outer steel tube, and the inner steel tube will actually host the nuts, and the beam will be getting connected directly into those nuts. Just like a blind bolt, but it is not really a blind bolt because blind hole has some shortcomings. Here the nut is safely, securely present inside this inner steel tube. However, when we were doing the experiments, it is not giving a rigid joint which the code is expecting. It is falling in this semi-rigid zone. We are having some modification, so research is still going on. And coming to the myth busters, maybe I will just take a couple of minutes. So some people have the question like, concrete curing and hardening will be an issue in CFST. Since we are having the steel tube, how are we going to cure the concrete? So the answer is, there is no need for it. No need for concrete curing. So it has the adequate water content which is needed for hydration, and you don't have to, and it is, the water is not getting evaporated because you are having this steel tube encasement. So you don't have to worry about concrete curing. Of course, it will get hardened. We have done so many experiments. And concrete will corrode from inside. What about that? From outside, we can give all those corrosion protections. What about the inner concrete layer? It is having concrete which is having water, and that will get corroded. How are we going to handle that? So no free oxygen, it is not going to rust. So we don't have to worry about it. And there are also some test experiments which people have done in concrete filled CFT tubes and study the corrosive effects, which it is not showing very large corrosion effects. So concrete shrinkage will affect the composite action. So what about that? So there is a gap which is formed because composite action is all about when there is a contact. So a gap within 3% is manageable. It is still giving the same behavior, okay, the resistance, and also we have to provide the shear connectors if it is beyond that limit. And wet concrete effect. During concreting, you have this steel tube which is going to confine and everything is fine, but what about this hydrostatic effect, and which is going to bulge out your very large D by T systems. So in one of the studies, it was recommended that you have to use something like rings. You don't have to use full length formworks, but you can give some rings so that at least at the bottom height of your column, so that you can avoid this bulging effects during the concreting time. And exposed to steel tube for fire, I think we have already discussed about it, like how to take care of it. Definitely the fire resistance is better compared to bare steel sections, but we can also improve the fire protection just by giving fire protection for the steel. So in conclusion, for composite column design, we have to follow these considerations. First, we have to check for local buckling and all the other basic checks to say that, okay, this is a composite cross-section and I can use simplified methods of design. Next, we have to find the member resistance, simplified, or if it is not coming within those conditions, we can go for general design method. After we see that, okay, it is having adequate compression and also the bending moment resistance capacities, we have to make sure that the load introduction is properly detailed with shear connectors. And also, we have to find the correct shear resistance of those shear connectors. So consideration has to be, we have to give consideration for the joint type. We cannot blindly take some joint and then do a regular analysis and do the rest of the design. If it is a semi-rigid joint, you have to take those exact properties from the literature in your model, do the analysis for those properties for service case separately and for ultimate limit state separately, separate models, and proper design has to be done for those connections. And in N-case column, we have seen that even though the local buckling is effectively reduced, if you are having an I section of so-and-so sort, the global buckling is affecting your utilization ratio compared to your CFST. And care has to be taken in CFST when we are going for concreting and fire resistance. A lot of detail is given in the codes, Eurocode as well as American code, like what kind of care, particularly in the commentary section of American code, very good recommendations are given. Thank you.